Okay, so good morning again, everyone. So today I'm going to talk about the emission inventory and also air quality modeling. Actually, these two things are the tools that we use to manage air quality in different locations. But anyway, to better explain of these two, I will use the case study of the modeling of black carbon deposition on the Himalayan region over the glacier in the current and future climate to be the case study to explain how can we set the air quality model and also how can we apply the emission inventory into the study area. Okay, so the outline of this presentation, first I'm gonna talk a little bit about the air quality management. So how can we manage the quality of the air? And then we will go to different tools that we use in air quality management. Um, then I will use the case study to explain how air quality management can be done by using air quality modeling. I will start with some background about the study. Then I will talk about the model setup, and then I will skim over it. Go to talk about the scenario, which is going to be in the part of one tools that we're going to talk about modeling. Then we're going to talk about the emission inventory that I use to put into this model. So we're going to talk about emission inventory, which is the second tool. And then we're going to talk about model validation, because after we run the model, the output of the model should be validated with the monitoring data. That's why the third tools in air quality management come into the place now. So we have modeling, emission inventory, and also we have monitoring. After that, we're going to talk about some implication of the result from the model, and we'll go to the conclusion. Okay, so air quality management usually involve both the control of air pollution at the source and also the effective dispersion of pollutants in the atmosphere. Anyway, these two phrases actually pretty much the same thing. When we're thinking about air pollution control, we prefer to control the emission at source. However, there is another method that we can use in order to reduce the emission from the source too. And we usually dealing with some of the effective dispersion of the pollutant. For example, in the case that we have industry, we have emission from the stack, right, from the industry, and then those stack release the pollutant into the atmosphere. And then if we think about the people that usually going to be the one that get the result of those kind of pollution, get the impact from the pollution, the first thing that we can do to minimize the impact to the people is to reduce the emission at the source. So that refer to control at the source. And the second one, we can use any process in the atmosphere to reduce those kind of pollution. Meaning that, for example, if we have very high stack, instead of have the low stack, and then we have high stack, and then we release the pollutant out from the tip of the stack, and then those pollution before it reach people, then the concentration going to be lower, right? Because usually the concentration in the air of any pollutant going to be in the unit of microgram or gram per cubic meter of air. If we have higher stack before the pollutant reach the ground or reach the receptor, then the volume of the air that mix with the concentration, with the amount of the mass, going to be larger, so that the concentration going to be lower. So to go back into this idea, anyway, the method that we use to control air pollution from the source itself, and also use some improving of the dispersion so that the pollution level that will reach the people going to be lower. And there are different types also of the air quality management program and also management. It depends on the location that you would like to apply this kind of air quality management. When we're talking about the ambient air, like outside of the building, then usually we will manage this air quality with the regulation. Like for example, like the government going to be apply some air quality, like the emission control or some ambient air quality standard or something like that. And if we live in the workplace, then most of the workplace that have people sit together, come from different locations, then we need to have common rules, right? The regulation, and sometimes they also have the guideline. Okay, if you do this, then it's going to impact to other people. Then they just suggest that you should not do those kind of activity or something like that. So for the workplace, we can also do by regulation and guideline, but most of the time, the regulation gonna be coming first. Next thing gonna be indoor air pollution. When we're talking about indoor air, meaning that the location are enclosed, like for example, in your household, even though you spend most of the time indoor, and then maybe we need to be more concerned about indoor air pollution. But again, indoor is more private, right? So people live in the household, and then maybe the government don't want to maybe regulate something. So most of the time, the way to manage the air quality inside or indoor area going to be based on the guideline. So the suggestion before the regulation, because we talking about the privacy here. Then last one going to be the exposure due to some personal activities. For example, like some people smoke, something like that. Right now, I think we are moved toward the regulation more than the guideline, right? Because in most of the country, they also don't allow you to smoke like outside of the building or some inside of the building, and also some area they will allow you to smoke in some designated area only. So these are different types, but mostly going to be based on regulation or the guideline that we can use to manage air quality in different locations. Okay, talking about the goals of air quality management, the first one is to eliminate and reduce the ambient air pollution concentration to the acceptable level. This acceptable level can be any level that may be set by the ambient air quality standard of the government, or if the government would focus only on the health of the people, maybe they can look to this information through the WHO level, so that it's going to be very low concentration that it will be exposed to. And also for the rest of the point, going to be the avoid effect, adverse impact to the human, to the animal, to the plant, and also to avoid the damage to the material. So these are the goals of air quality management. The first one is to reduce or eliminate the ambient pollutant to be in the acceptable level. Those acceptable level going to be in the level that it will not impact to any of the living organism and also some material or the building. Okay, when we're talking about the integrated approach for air quality management, we need to consider both cause and effect, right? Cause and effect in this case, when we're talking about air pollution, we're talking about the source of pollution leading until the end is the health risk of the people. But most of the time, we are not going into that end. For example, like my research usually start from the source of air pollution, then end at the concentration in the atmosphere. And then there's going to be other research group that continue the study from concentration in the atmosphere until to the health risk of the people. So those things usually not integrate together. But in order to get the better air quality management, we need to have system or the process that consider from the cause to the effect, which is the health risk, then starting from the source of the emission, so that we can see the picture, the overall picture of the system. And then the recommendation is we need to focus first on the key pollutant and also the key sources, meaning that most in developing countries, we have a lot of problems of air pollution. We may have problem of ozone. We may have a problem of particulate matters, maybe CO, hydrocarbon, and so on. But those things, we need to prioritize the issue that we have, which pollutant that we need to reduce first. And there are going to be a lot of criteria that we can use to select different pollutant or different source that we would like to reduce the emission first. That brings to the next one, like maybe we need to consider about cost effective of the action. Sometimes, even though we can reduce the emission from one source, but the cost is too high, maybe that is not the cost-effective action. So we may skip those kind of action first, and then maybe go to some other source that easy to reduce emission, and also in terms of the budget or the funding that we need to spend, it's also cost-effective. And then we need to consider both policy and technical issue. Sometimes it's very easy that we can apply the technical advancement to reduce the emission. But in terms of the policy, we could not do that. For example, if the government said that, okay, to reduce emission from car, we ask all people that want to use car, they need to install the control device, which costs maybe one third of the cost of the car. So most of the people cannot do that. But in terms of the technical, it can do it. It can reduce the pollution. But no one can do it because the cost or the price is too high. Then we need to have some policy in order to apply those, in order to smooth the process that people can apply. For example, maybe reduce the cost of the income tax of those kind of equipment or something like that, so that people can have cheaper price to install this kind of equipment. And then last one, this one put in the last but not the least, we need to have the dissemination of the air quality data so that we can raise the awareness of the people. The people can be support for the air quality management. So in this context, I think not only air pollution, but also all other environmental problems that we need to take this into consideration. If we want to move the control or the system into the way that we can control better environment, then we need to make sure that the public have the support on this. You can see in different example that when we have the people that have more concern about environment, or of the regulation or of the participation of the people make the progress of the maybe the standard or the regulation move faster than the case that people don't have awareness from the environment on the environment. Okay, when I talk about integrated approach, so we can see in this picture that how it works. So if I start with the area that I don't have idea on what is the current condition of air quality in that situation, in that area. So I will start with setting up some of the monitoring station. So those monitoring station will tell me how good of the air quality in that area. So I will get the ambient concentration information. And then with that information, people can estimate the exposure. How many people have exposed to this concentration of pollutant in different locations, and then we have exposure of the people. And those exposure can link to the health of the people in different locations. Then if we know that in this area, people have high exposure and also maybe have high health impact, then we would like to reduce the exposure of the people by maybe reducing the level of air pollution. We can do that by using air quality management system. And those, as we discussed earlier in the previous slide, we need policy measure and technical measure at the same time. And after we come up with the policy that are appropriate in the situation, then we need to apply those policy to reduce emission at source. For example, we would like to reduce, we found that in the area, maybe the emission majorly coming from industry. So we may apply some policies to reduce emission from the industry by 50% or something like that. And after we apply those kind of regulation, also we need to check the ambient concentration, whether it can, whether the regulation that we apply can be, is effective or not. Then this is the loop of the system for air quality management. Okay, put into more detail, because last time we're talking about air quality management, and now we're talking about the step. The first step to develop the air quality management program in any location is we need to collect the background concentration. This background concentration gonna be the social condition, economic condition, the cost benefit of any control option that we will use, the health impact of the people. For example, what are the current particulate matter concentration, and also how is that related to the number of people that admit into the hospital or something like that. So those information need to be collected, and then we can design the air quality management program. So first, we need to set goals. So we need to set ambient air quality standard first. So we set ambient air quality standard that, okay, in the ambient, the concentration of specific pollutant should not be higher than this. And then to confirm with this ambient air quality standard, we set the monitoring station, right? The monitoring station will give you the concentration of the pollutant in the area, so that you know whether the concentration of the pollutant in the area can be confined with the standard or not. Then you check whether it can attain ambient air quality standard or not. And then if it already attained the ambient air quality standard, then maybe you need to think about whether we should revise the ambient air quality standard to be more tightened, like lower the level of the available standard, so that maybe we need to control better in the system. And also, if in this case, the ambient air quality standard from the monitoring data tell us that right now the ambient air quality is not attained, is not past the regulation, or is not past the ambient air quality standard, we need to think about the source emission control. How can we reduce emission from different sources in the area? And we can do that by doing the emission inventory. The emission inventory will tell you how many sources are available in the area, and how much of emission that come from each sources. And then you put this emission inventory into the air quality models with the information of meteorological condition put into the model, and the model will give you the concentration. And then you compare this concentration with the ambient air quality standard, that when you reduce the emission from specific sources put into the model, what will be the new concentration, and whether the new concentration is lower than the ambient air quality standard or not. So this kind of the general step that we use different tools in air quality management, and we will talk about the tools in the next slide. So the one that I highlight here, monitoring, source emission, and also model. These are the tools that usually used in air quality management. Okay, this is the to put into more detail about technical tool for air quality management. The technical tools that we use to control ambient air quality gonna be first, ambient air quality monitoring. This one will give you the information on what are the current level of the concentration of pollutant in the area, and then how to report the data so people can get awareness of particular pollutant in those areas. The second one gonna be the emission inventory. This is gonna be the tool that provide you the information of the type of the source and also the amount of air pollutant that emit from the source in your area. And then the third one gonna be the modeling, or the models that you will use to estimate the pollutant concentration using mathematical equation. And this will give the overall picture of the air quality. Anyway, these three tools, monitoring, inventory, and also modeling, are interdependent and are complementary component of the integrated air quality management. Okay, those are the general information about air quality management, but I just want to remind you that usually there are gonna be three tools that we use to study and then come up with the policy in any location. The first one gonna be modeling that we're gonna talk in this presentation. The second one gonna be inventory that we need as the input into this model. And then the third one gonna be monitoring. Those monitoring we're gonna use to validate the data, to validate the output of the model. So I will try to explain each component for air quality management by using this case study. This case study again is the modeling of the black carbon in the air that deposit to the Himalayan glaciers during the current in 2013 and also in the future climate system. A little note here that this study is the work done at the Atmospheric Environmental Research when I work in the US, and this project is already published in the JGR Atmosphere in 2018. Okay, first about the background of the study. The study area, we focus on Himalayan glacier. So this Himalayan glacier is cover the area of Himalaya, Karakoram, Hindu Kush, or I will refer to as HKHK in this presentation, which is the mountain range that passed through six nations like India, Pakistan, Afghanistan, China, Bhutan, and Nepal. So it is in the mountain range in this area. And then this area covered with ice with about 60,000 square kilometers of ice, which is cover that have contained the ice more than any other region outside of the pole. However, the problem that in this area it has already experienced with 1.5 degree temperature increase. So it also experienced with the glacier retreating. And this one also affects the stability of the water resource in this location. Talking about the importance of the glacier, when we have the snowfall and also the glacier melts, this one is the important process to control on the timing and the availability of the water resource in the area. The glacier itself helps to moderate the river flow in the region that provide the source of the melt water during the hot and dry year and also store water during the colder or wetter year. The dependence of the glacier and the snow make the river in the area particularly vulnerable to the climate change. So in general, if we're talking about importance of the glacier, during the period that we have more water or more deposition of the ice, then the glacier will make as the reservoir of the water. But during the hot or dry year, the water going to be melt from the glacier and provide the additional water into the river, so that the glacier work as the buffer for the availability of the surface water in the area. Then why we need to focus in this area? Because not only the glacier retreat because of the increasing in the temperature, but in this study, we will study one of the impact on the glacier, which we believe that is one of the major impact to the retreat of the glacier, which is the black carbon deposition on the glacier. The black carbon maybe give you a little bit of information of the black carbon. Black carbon is the particulate matters that usually form during the incomplete combustion of the biomass and also the fossil fuels. For example, if you go walk along the street and then you see the tailpipe of the truck or the bus that didn't have well maintained, you're gonna see a plume of black smoke coming out. Those are considered as black carbon. So black carbon also can be coming from biofuel in residential combustion, can be coming from coal, can be coming from different type of diesel combustion or gasoline combustion from on-road vehicles, can be coming from off-road vehicles like the tractor or any engine that didn't use on-road. And then it can come from combustion of industry like coal, brick kiln or something like that, and also from open biomass burning. In this study, we interested in the black carbon deposition on the glacier because if you see the glacier, usually the glacier gonna be white color. And when we have the incoming solar radiation with the white color of the glacier, usually it's gonna be scatter the light or scatter the incoming solar radiation, right? So when it's scattered, the temperature of the surrounding environment gonna be cooler. So the glacier not gonna be melt. Anyway, if we have black carbon deposit on the surface of the glacier, as you can see here, right? This color change from bright white color to dark or darker color, black or darker color. And this color, when it change to dark or black color, meaning that when we have the incoming solar radiation, the solar radiation will not scatter as much anymore, because when you have any dark object put in front of the incoming solar radiation, it will absorb the light, right? So now instead of scatter the light, keep temperature of the environment cool, now it absorbs this when it covered with black carbon. It absorbs the light incoming solar radiation and make the temperature of the whole system increase. And also with the surface that have deposition of the black carbon itself, it absorbs the light, absorbs the energy from the sun, then it starts to be melt. So there are two effects. The first one, it melt because the increase in temperature of the glacier that also have the black carbon deposit on it. The second one is the melting because of the overall temperature of the system is also increasing. So that's why we are interested in the black carbon deposition on the glacier. And then in this case study, we will model the wet and dry deposition of black carbon, meaning that we will model, because black carbon is the particle, the bioparticle itself, it have a weight so that it can be pulled down to the Earth's surface by gravity. Those kind of process we call dry deposition. And another process that maybe we can remove those black carbon by rain or by snow, those process called wet deposition. So in this study, we will model both wet and dry deposition of black carbon to the HKHK region during two conditions. The first one going to be current condition, and the second one going to be in the future if we change some of the emission from different sectors. So that are the general information and the case study that I will use to explain the modeling system that I will talk about, also emission inventory and also monitoring that used in the model. Okay, for the overall air pollution modeling, because now we're going to talk about modeling, so I just give you information about air pollution modeling a little bit. Why we need to do modeling in environmental engineering? The first thing is because the environmental system is very complex, right? If we're talking about air pollution, we're talking about one pollutant in the air. But when we want to model those pollutants, whether it moves from one place to another place, whether it deposit on the ground or something like that, it's not only we need to model those particular pollutants. It has some chemistry that make a reaction in the atmosphere, and also there are wind or pressure or maybe humidity in the atmosphere that also impact to that particular pollutant. So that is very complex. The model that we use is the tools that we use to integrate those kind of process together, and we can be explained by using some systematic approach. Usually we use mathematical approach to explain those kind of phenomena. And then the model can be predict what happened in the past, what happened now, and also what happened in the future. Okay, in terms of air quality management, there are two major type of model that we usually use. The first one we call Dispersion Model, and then the second one we call Receptor Model. And from this chart, you can see that in air quality, usually we will interested on the source or the emission, where the emission coming from, like emission coming from mobile source, from industry, or maybe some other area that emit emission of the area source. So we're interested in the source, and then another one that we're interested in is the concentration at the receptor. How much is the concentration will be reached, like people, or maybe which city or something like that. So there are two types of the model, as I told you here, dispersion and receptor model. The dispersion model is when we know the concentration, when we know the emission from the source, right? We know that how much emission come from mobile source, how much emission come from industry, how much emission come from area source, and then we put those information into the model with the chemistry in the model and auto input as input another meteorological condition. This will give you the concentration at the receptor. So this one called dispersion model. You know source, put into the model, you get the concentration. And on the other hand, another concept of the receptor model is you make the monitoring at the receptor anywhere that you want to know where the pollution coming from. You make the measurement, you got the concentration, and then you put into the model. And then the model will have some chemistry information. The model can give you where is this concentration coming from. Maybe 50% come from mobile source, 10% come from industry, and another 40% come from the area source, and so on. So two types of the model that we will use in air quality management. And in this presentation, I will focus on this kind of dispersion model. So you will input source information as emission inventory. We will put some meteorological data, and then we would like to see the concentration at any location. Okay, again, this is the general information of the air quality modeling system that we use in this study. So this is the model system. We can identify any location, any study area, and then usually we put it in different grid box. The input to this model going to be the emission data, emission inventory, the land cover data, and then the chemistry mechanism that happen in the atmosphere for different pollutants. And then we're going to put in the meteorological data, which usually we also get it from another meteorological model. So all of this going to be put into the model, and then the model going to give you the concentration. This concentration, before we can use this concentration in any publication, or maybe before going to the giving this to the public, then we need to compare this concentration with the monitoring data first, whether the predict concentration is in the good range or not. So again, I would like to emphasize that for the air quality model, we need to have emission data or emission inventory. We need to have the modeling system, and then we need to have monitoring data. So this is three tools that usually we use in air quality management, and also use as the input for air quality modeling. Okay, back to the case study. The model setup, I will not go into detail about this. The primary model that we use is going to be we call WolfChem. It is the weather research and forecasting model with copper with the chemistry. So there are two parts in this model. The first part is WolF. This one is the meteorological model, provide met data like the wind speed, wind direction, temperature, pressure, what else? The rain, also snow, something like that. And also the second part going to be chemistry, whatever chemical process that happen in the atmosphere that will change the concentration of the pollutant. And these are the input list of the input and assumption that we put into the model. I will not go into detail about this. So now I'm going to talk about the model scenario, because in any model, we would like to know what will happen, maybe current or maybe in the future. In this model, we run model for 4 years, January, April, July, October in 2013, and also during 2040 to 2015. We select this year because it represents different monsoon. In January, it refers to winter monsoon. In July, it refers to summer monsoon. And April and October is the transition period between winter to summer and also summer to winter. For each period, we run the model for 20 days. We use 14 days as the spin-up data, and then we use another 14 days for data analysis. So we will use only 14 days in each month for data analysis. And then for the scenario, we did for two scenarios. The first one going to be current condition with base year in 2013, and then the second one going to be future condition with the base year in 2040 to 2050. And then because we are dealing with the future condition, then the emission and also the consumption of all fuels, we're going to be based on the RCP. This RCP going to be the project of the emission from 2010 to 2100. And this RCP 4.5 also used in the IPCC report for the climate change report, so that the result in this study can be used to compare with other studies. Okay, and then another part that I talk about is the emission inventory that we need to put into the model. So we will talk into the model in a little bit of detail on emission inventory. The emission inventory is the comprehensive list by source of the air pollutant emission in the geographic area during a specific time period, meaning that the emission inventory will give you the information about where the pollutant coming from, or the source of the air pollutant, what type of pollutant, for example, NOx, particulate matters, or CO or something like that. And then in that area, so if you put the boundary that, okay, you want to study the emission inventory in this area, only the source that are in this area going to be included in the study. And then what time that you're interested. Maybe currently in 2010, in the future in 2030, or in the future in 2050, and so on. The purpose of the emission inventory, the goal is usually to obtain the information of the category and also the distribution of the source of pollutant. And also it will give the information on the amount and then the type of pollutant that it emits from different sources. And then the question is why we need to do the emission inventory. The first answer is to identify the major source, to identify the cost-effective control strategy, permitting, and also emission fee, as we discussed in the overall air quality management system. The second one, we can use emission inventory as the tool to track the emission over time. Sometimes we can estimate that whether the emission going to be increased in the future or lower in the future. If we see the trend by doing the emission inventory in maybe 2010, 2015, if we see the trend that is going up, then maybe we can expect that in 2020, the emission also will go up if we don't apply any control measures. And next one is going to be the one that we focus in this presentation, that we're going to use it as the input for the modeling activities. Then we can use the emission inventory to design the monitoring program. We can do the emission inventory first, that where the pollutant are coming from, and then the location that have high pollutant, maybe we put the monitoring station over that location. And also last one, which is also very important, we can do this to inform the public that where are the pollutant coming from. And then we can tell them that, okay, in the city that we interested, most of the pollution are coming from traffic. Then if we want to reduce the emission, maybe we need to reduce the use of the car in the city, and then we ask people for collaboration and so on. So the basic formula of the emission inventory is going to be emission factor multiplied by activity data. This emission factor is the rate of emission that released from the source per the activity unit. It can be any unit, like for example, kilogram of sulfur dioxide per ton of coal burn, like the emission factor. And the activity data is the amount of activity per time period of the emission inventory, which correspond to the emission factor that we use. For example, if the emission factor that we use is in terms of kilogram of sulfur dioxide per ton of coal burn, then the activity data that we use is going to be in terms of the amount of the coal burn per year. So that when we multiply these two products together, the emission inventory in this case is going to be kilogram of sulfur dioxide per year, right? Okay, that are the general information about emission inventory. And emission inventory is one of the required input into the model that we will use in this study. So emission inventory that we use in this case study, the emission inventory that have black carbon, because we want to we interest in black carbon, and also other co-emit pollutant, because there are some reaction that appear in the atmosphere to be increasing in black carbon formation or reduce the black carbon concentration in the atmosphere. So these are all of the list of the pollutant that we put into the model. The emission inventory we use from RCP that used for IPCC report. We use from Eclipse and also Winijkul in 2016. And this Winijkul we will talk more into detail because it is one of the study that I conduct research on the residential emission. So in this case, RCP, because we want to keep the total emission on the same scale as the IPCC report, so that the emission result in this study can be compared with other study if they use also the same projection like RCP projection. So RCP will provide total emission, but the breakdown or disaggregate of emission into different sectors will be based on the Eclipse and Winijkul database, because this RCP usually going to be provided in terms of the total emission. So the sector that that we include in this study going to be industrial group, diesel group, open burning, and also solid fuel group, that we would like to see the impact of this group on the black carbon into the study area. And then two emission scenario that we will focus in this study going to be no further control, which refer to the case that for the current registration, there will be no further registration that dealing with the emission control after 2015. In general, there will be no other control after 2015. After 2015, the technology is going to be the same. No control implement after that. And then the second scenario going to be mitigation scenario, or we call MIT, that we're going to refer to this as the measure that we're going to refer to this scenario as all of the measure going to be applied after 2015, and then we're going to compare the benefit of these two scenarios in the future based on the black carbon deposition in the study area. Okay, so I will talk more on the residential emission, which considered as the inventory that developed based on the to estimate the concentration, to estimate the emission from residential sector. In the residential sector, in this study, we include cooking, heating, and lighting emission. Okay, I do this emission inventory by starting with the question. First, if I know that how much fuel consumption that people use in household in different locations in the world, but I don't know where in that city or where in that country where people do use those kind of fuels. For example, I don't know where people use solid fuels, like where people use for biomass fuel for cooking, where people use coal for cooking. I would like to find a way to help me to allocate this type of fuel from the national level fuel into very small scale, very local data. So I use three global maps. First one is the urban extent map. This map I use to identify the urban area. The second one is the nightlife map. I use this map to identify whether people have access to electricity or not. The third map that I use is land type, so that I identify whether people live close to the forest or not. Because this is important, because from different literature, we found that if people live in rural area in developing country, people, if they live close to the forest, for example, live within 5 kilometer boundary of the forest, they will tend to go to the forest and collect fuel wood from the forest, because it is free fuel that they can use to cook and use for heating in their household. So then the methodology in this emission inventory is I identify by matching population with the resource that are available in 5 land types. I start by population map population distribution map. Then I use 3 maps that I showed you in the previous slide, like urban area map, nightline map, and also forest land cover map to identify urban area. So I separate people into people living in urban, people living in rural area. And then for the nightline map, I separate people that live in rural area that have access to electricity and in the area that don't have access to electricity. And further, I use the forest land cover and then project 5 boundary from the forest to be the forest access, assuming that in those areas, the people will go to the forest or collect fuel wood to use in the household. And then I separate these rural electrified and rural non-electrified into electrified area, forest access and non-forest access. The people that live in rural area that have forest access, they tend to use fuel wood in their household. Okay, this is the equation that I use to calculate emission. They're going to be different. You can see that maybe it's complex, but anyway, if we go back to the same equation that I showed you at the beginning, it's going to be the same. Start with the amount of population that use different type of fuel and different type of end use, whether it's cooking, heating, or lighting. And then the second term going to be the term of energy consumption to cook food, to heat food, and also for lighting. And then last one going to be the emission factor that we use with particular activities. And this is the spatial distribution of 5 land types. So the land type that have urban area and then 2 rural area that have access to electricity and 2 areas that don't have access to electricity and have access to forest and don't have access to forest. As you can see here, most of the area in this world gonna be either green or gray, right? So meaning that most of the city, most of the area in the world gonna be the area that don't have access to electricity. And most of the area that marked as green here gonna be the area that have access to forest. Then fuel wood gonna be the major source of fuel that used for cooking and heating in this particular area. And in this study, the emission inventory in this area, in the south area, going to be used, put into the model, and then we're going to be used as the emission input for the model. So going to be skip this one. And this is the output from the study of the emission inventory. Like this one is only particulate matters. The red color refer to the location that have high pollutant. So you can see that in this area, we have high pollutant emission from cooking because it's the area that use solid fuel for burning. And this is the area that emission data that we will put into the model. Okay, so after I put those emission inventory into the model and then I run the model. And then before we can use the model to estimate the concentration, the first thing that we can do is we need to validate the model first. So we validate the model with the observation data or the monitoring data, which is another tool that we use for air quality management. The Wolfram output in this case study in 2013 was 1 and also compare with the observation in terms of the surface concentration, black carbon concentration, in terms of the surface temperature, and also in terms of the surface precipitation. So right now, this one is the table. As you can see, different location. The one that in bold is the location that in the study area, in the HK region. So you can see that this work refer to the output from the model is the black carbon concentration. And observation is the monitoring data that we get from monitoring station in different locations. And you can see that if we compare this during different time of the year, you can see that the output from the model and observation are pretty much okay within the same range. So we can summarize that the model can capture the geographical variation of black carbon concentration over the Southeast Asia. Anyway, we can see some of the large difference in terms of underestimation in this monitoring station. some monitoring station, when we compare the concentration with the model output, it's going to be different. But anyway, in general, is show the model can capture most of black carbon concentration. The second step that we compare, we also compare with the observation by the satellite. We compare the surface temperature. The left picture here is the output of surface temperature from the model. And then because we want to compare with number C here, C is the surface temperature that coming from the satellite measurement during the same time. So we project A, which is the fresh or the raw output from the model, into the scale that is the same scale as the measurement from the satellite, and then we compare together. As you can see that they are pretty much the same. The model can capture the same distribution of temperature. Like you can see the high temperature over India, and then the cold front here, cold temperature over the HK region, which also show the same from the measurement data. The third one that we compare with the actual data going to be the surface precipitation in terms of rain and also snow. So we have the WRF-Chem output here, and also we compare with the TRMM precipitation, also the satellite measurement. You can see that actually the variation is the same. The variation between months is pretty much the same, because you can see the color between the WRF-Chem output and TRMM is pretty much the same. But anyway, if we see about the color scale, we can see that usually WRF-Chem in this study predict higher precipitation, which later you can see that we predict lower concentration of black carbon in terms of wet and dry, wet deposition, because more precipitation estimate. Okay, after we compare the result with the observation, then we run the model for the case of 2013 input, the emission inventory, and then we study the result. So this is the result of BC deposition in terms of microgram of BC per square meters. You can see that this is the study area, and then the white color refer to the boundary of HK region, or the region that have the glacier. So the BC deposition in this case, when we're talking about, you can see that BC deposition are mostly, so the red color refer to high BC deposition, and then lighter color refer to low BC deposition. You can see that most of BC deposit in the area that they emit pollutant, right? So you can see that in India and outside of this white color, because in the white color is the glacier area, don't have sources. So most of the deposition gonna be in the area that emit the pollutant, but there are some black carbon deposit in the area of the HK. And then if we interested to see whether the fraction of BC that deposit in this HK area are coming from the area inside inside of our study area or outside of our study area. The left-hand side here is anthropogenic in the area. So anything from India or something that are in this box, how it impact to the HK area. The second one gonna be biomass burning or forest fire that come from natural source, how much it impact into this HK area. And then the third one gonna be outside of this boundary, how much of emission from country outside of the study area that impact to the BC deposition in this area. And you can see that on the right-hand side, if we focus only in the area that within the boundary of white color, you can see that most of the deposition compare between on the right color here, compare with the left color, left figures, and also the middle figures. You can see that most of the deposition of BC in this HK area are from the area outside the boundary, meaning that most of the emission of black carbon that deposit in this area in this HKHK area are from outside of this area, not from India, not from the location that are close by, like not from Nepal or something like that, maybe from China or maybe from Thailand, Myanmar or something like that outside of this boundary area. Okay, for the current climate, we also estimate, after we estimate the concentration, we divide black carbon concentration over the precipitation, and then also we estimate the mass fraction of BC in snow, because we want to know how much of BC that deposit in the snow, and that will tell us how much of the impact of the BC that will change the absorption of the incoming solar radiation, right? And then you can see that from January to October, we can see different range. So on the top, it's going to be snowfall only. On the lower figures, going to be the mass fraction of BC over snow. So you can see that there is the large variation of the BC over snow over different time of the year. But anyway, when we compare the result on the right-hand side, this table, we estimate the concentration as referred to this work in January, April, July, October, and then we create mean average from this study in different locations compared to the observation. So there is the researcher that go out and then collect the snow sample and then measure, analyze the BC concentration over that sample. And then we can compare, and then most of the time you can see that the concentration from the model going to be lower than the concentration that they come from observation. The major reason is, as I told you, that we overestimate the snow in the area, so that when we divide black carbon over the snow, then the mass fraction going to be lower, which is the output of this model compared to observation. So that is the result of the current condition. You can find that the BC concentration itself agree well with the monitoring data, but because of the overestimate of the snowfall in the area, then when we estimate the concentration in terms of the mass fraction, our model underestimate compared to the observation. And then for the future climate, so that is the one that I already finished, is the current climate in 2013. For the future climate in 2040 and 2050, we also run the model for two cases. The first case is no further control, like no other control after 2015. And the second one going to be mitigation, that we apply all of the control measure after 2015. And then we want to see the impact of the deposit in the area. So when we compare the output of the WolfCam in terms of BC concentration between no further control and mitigation scenario, the difference, you can see that is more than 60% of the concentration that we model as the model output in any site, meaning that usually mitigation scenario can reduce the concentration significantly compared to the case that we don't do anything. And after we put this no further control and mitigation into the model, and then we see the deposition of black carbon in different locations, in different season in January, April, July, and October in no further control and mitigation scenario. In general, both scenario show the reduction in BC deposition in the HKHK region or in the white color line boundary area. For the no further control, the emission is reduced, the deposition reduced by 33%. Mitigation, the BC deposition reduced by 55%. Talking about in study area contribution and also outside of the study area contribution, it is still the same that the BC from outside of the study area contributes significantly to the deposition of BC in this HKHK region. And if we focus on what type of source that contribute most to the deposition of BC in this HKHK region, for the no further control, the major emission source going to be from the industry and from the solid fuel, like from residential combustion. If we're talking about the mitigation measure scenario, then the contribution of industry going to be much higher than the solid fuel, but solid fuel going to be the second highest, contribute to the second highest of BC deposit in this HKHK region. Okay, last one, we also calculate the mass ratio in terms of black carbon over the snow. And then you can see that pretty much the same pattern of no further control and mitigation. But there are just some slight difference over the area of between the border of Nepal and China. Like in this area, as you can see, like over this area, this one they have high mass ratio of deposition, but this area they have lower mass ratio of deposition. But anyway, in general, the distribution of the mass ratio is about the same in two scenarios. Okay, about the implication of this study. This study usually produce the high resolution deposition map we can use to determine the impact of different sources on the BC, on the albedo of glacier in the HKHK region. And then further, we can use to identify how this albedo change affect the glacier melt and also how it will affect to the water availability in the region. And this study can help policymaker or maybe stakeholder in South Asia to understand what should be the local action and also the collaboration that they need with other countries outside of the study area. Because from the model, we tell that reducing only local emission from India, from Nepal is not going to help because most of the emission are coming from outside of the study area. So they need to have collaboration with outside of the country of this study area too, in order to reduce the deposition of black carbon on the glacier. So in conclusion, in this presentation, I would like to introduce the emission inventory and also the air quality modeling, which are the technical tools that we use to control air quality or manage air quality. And then another tools that we use as the subset in this presentation is also the monitoring that we use to compare the output from the model compared to the monitoring data. And then I use a case study to explain how can we use different tools like emission inventory, modeling, and also monitoring to manage air quality. So in this case study, we use model, which is WolfChem version 3.6.1 to estimate the black carbon concentration, concentration and deposition on the snow. And then the input that we use gonna be two scenario: emission input, no further control, and then mitigation scenario. And this no further control, even we don't do anything, but because of the projection from the RCP that we use show the lower in emission, then no further control gonna be reduce the black carbon deposition by 33%. And if we apply all of the regulation that we can use to reduce emission from air pollution in both inside the region, inside the region, the deposition of BC in this HKHK region can be reduced by 55%. So that the implication from this study that maybe we need to work, how much work that we need to put into reduce emission in different sectors, and where is the location that we need to reduce emission so that the BC deposition on the glacier in this HKHK region going to be minimized in the future. So with that, I open for the discussion and question. Thank you very much.
All right, thank you very much, Dr. Ekbordin. That was quite remarkable explanation. That's already okay. We will continue to the Q&A session. There's already 2 questions here, sir.
Yes.
The first is from Miss Isra. He said, is this modeling applicable to source of emissions from fugitive source such as forest fires? As we know that the largest source of GHG emissions in Indonesia comes from land use and land use change and forestry. What is the level of, and also the second question is, what is the level of accuracy of this model?
What is the level of what?
The level of accuracy of this model.
Okay, I think, thank you for the question. I think these 2 questions are very good. So the first one, to address the question whether this model can be used to address the problem of forest fire, the answer is yes. In different locations, there are the study that we try to put in forest fire emission, and then we want to see what will be the impact of the forest fire. And the movement of the development of the study in this that relate to forest fire, we try to input the output of the satellite data to identify the location of the forest fire. For example, today, if we have forest fire in this location, then we will incorporate those type of location with the land use map, like overlay with the land use map, so we know what are the type of the forest that get burned, so that we put that into the model, and then model can predict the concentration at different location maybe in the city or maybe in the country. And also this model can be, the scale that we can work on this model can be different. We can work on the city scale, we can work on the regional scale, so that we can see how the pollutant move from one location to another location, or one country to another country also. The second question is about the accuracy of this model. I think as you can see in this presentation a little bit, that there are some of the prediction that still, when we compare with observation, still is not satisfying. For example, like precipitation will be still much higher than the monitoring data. So in terms of the accuracy, I think it is acceptable, but anyway, in all of the application, when we use model, we need to compare with observation before we can use, because in this model, it is very complex model, and then we need to input a lot of input data. They will have different options that we can use as the input, so that some input may be suitable in your study area, some input may not be suitable in your study area, so that the output may be, the accuracy of the output may be related to the input that you put in. So to check the input, to check the output of the model, we recommend that maybe most of the time, you need to compare with the observation first, before you use, because the accuracy of the data depends on the input, and it can range from very good to maybe not represent of the emission in that location.
All right, sir.
Yes.
Okay, sir. Regarding the model, there's a couple of questions regarding about the software you use in the modeling, sir. Perhaps you can tell us about the software, and is it openly accessible to people, sir?
The model called WolfCam, right? So the model is freely available on the website. I think on the NCAR website. It has 2 components, as I told you. The first one going to be Wolf, that component that dealing with estimation of meteorological condition, and the second part going to be the model that predict the concentration of the pollutant in the atmosphere. And this model is special because we call it online model. Online model meaning that there is the interaction between the Wolf model and also the chemistry model. For example, today, if I predict the concentration of black carbon at very high concentration, so that in general, today is going to be very foggy day, right? Have a lot of black carbon. So because a lot of black carbon, then the light that coming in cannot penetrate down to the earth or something like that. So that today we don't have much incoming solar radiation, and this not much incoming solar radiation will feed back into to the WRF part, that for the prediction of the meteorological condition and also the concentration in the future or the next day. They will account the process that today they don't have much incoming solar radiation, so the reaction in the atmosphere may be reduced because not enough energy to activate those kind of activity. So this one we call online model, so that there is the interaction between the work part and also the chemistry part. But if you can see, if we have this kind of interaction, then the computational going to be very computational intensive. So the hardware that you need going to be very intensive. There is other type of the model, for example, the WRF, CAMEX, or something like that. That also the couple between WRF, which is the meteorological model, and also the CAMEX model. This one called offline model. There will be no interaction between WRF and CAMEX. WRF gonna provide meteorological data, and after that put in the CAMEX model, and then model gonna be generate the concentration based on the batch of the WRF output. So those are offline models, so that there will be no interaction, and then the computational requirement gonna be lower than the WRF chem. So in this case, the WRF chem model is free model available on the website, but because it is have the interaction between the WRF part and also the chemistry part, then when we want to use this kind of model, it need to have good hardware.
All right, sir. I have a simple question actually, sir. You said it was online, so can we interact our outputs with other people outputs, sir? So that we can make the comprehensive map.
You mean that like for the map output, like for example, if I study in the area of maybe Thailand, and then whether you study in the study of
perhaps
maybe
like that,
Indonesia. Sir. Actually that is interesting question. We can combine the result, but anyway, I think before we go into that conclusion, the first thing that we need to understand together or agree together that the input that we need to put in need to be the same. Right? Because in terms of the chemistry that happen into the model, I can choose chemistry 1, chemistry pattern 2, chemistry pattern 3, or something like that. So if we want to combine map together, I think yes, we can combine, but maybe the input that we put into the model need to be synchronized, so that the period that we overlap the data should be synchronized, will be synchronized together.
All right, sir. Okay, sir. We proceed to another question. Maybe there is a question from Mr. Adit. Sorry. That was a good presentation, sir, and I am interested in snow deposition in Himalaya. We know that composition of the snow represent the condition of air at the time snow formed. So can we know about the past condition of air based on the difference of the top and bottom of the glacier?
So this is a very good question, and I sorry that I don't have answer to this because I'm not involved in the observation part. But anyway, this one was put into one of the limitations in our model running. And thank you for asking this question. Because as you state that the deposition of the black carbon in snow is going to be depend on the concentration at the time that the snow drop, right? And also after the snow drop to the ground, they're going to be the process itself, because it's not black carbon not going to be always just stay in that snow. Sometimes it go down into the deeper level or something like that. So that things may impact to the observation. Like if you maybe if you collect for maybe 10 centimeters, 20 centimeters, or 30 centimeters into the different deep into the glacier, you're gonna get different concentration of the snow related to those the concentration of the black carbon during the time that snowfall. But in the model, we don't have that kind of information. We just run model on the time. We just run the model. What is the concentration of black carbon, and then what is the amount of precipitation during that time, and then we just divide those kind of things, which is cannot represent the actual situation that happened in the black carbon deposition on the snow in the actual case. But that's a good question. So I think if you want to compare maybe apple to apple, maybe when we do observation, we need to make sure that we put some of these into consideration. Because right now when we compare, we just look at the data in the past, that whether there are some people that do some observation data, and we try to compare those data. Maybe the method that they use to collect the sample for the observation maybe not applicable for the method that we run the model. But so I don't know. Sorry that I don't have the good answer to that question right now.
Still a good answer, still though. Thank you very much, sir. There's one coming from YouTube. A question from YouTube from Miss Indah. She asked about the mitigation. Maybe that is based on your experience. What mitigation that have already been done to reduce the impact?
Yeah, so actually you can see from the presentation that there are two parts that we interested. The first one going to be anthropogenic emission that coming from the study area, meaning that the country that surround this Himalayan glacier. And also another part is the emission that coming from outside of the country that surround the Himalayan glacier. And we found that the major part going to be the contribution from the outside of the study area, meaning that not only control of the emission inside the study area can reduce the emission of the black carbon in that Himalayan glacier. So first thing that maybe in terms of the mitigation, maybe the international nation need to agree on the term that, okay, if we want to save this glacier, every country need to reduce emission on their own country, because not only the country that surround those kind of glacier will contribute, and also the emission from outside those areas also impact a lot, much more than the country inside the area, maybe because of the wind direction or the meteorological pattern and so on. But if we want to focus on the sector that we really need to reduce, first gonna be residential cooking. As you can see that in the emission inventory, in India, in country that surround the HKSK region, the emission from residential is very high, because in that area they still use like very low quality fuel, like use wood, use coal for combustion. So those emit a lot of black carbon. The second one gonna be on-road emission, especially the diesel vehicle that emit a lot of black carbon. And the third one gonna be the industry that emit the pollutant in those areas. So there's gonna be three sectors. The residential sector and also the industry sector. But more importantly, going to be the reduction of emission outside of the study area.
All right. We still have a couple of minutes, actually. Maybe you proceed with another question. There are two more questions, but maybe we can combine it with one answer, sir. The first is from Miss Nuzula Elva. Dr. Ekbordin, in MIT scenario, how do you incorporate all measures into the modeling? Are there any assumptions that you develop? And the second question is from Miss Dewi. Is there any modeling for blue carbon, sir? You can answer that.
For which one?
The last one is she asked about modeling of blue carbon, sir.
Blue, maybe BLUE, blue carbon.
May I beg your pardon, sir?
Blue carbon or
She wrote blue carbon.
okay.
Mungkin Bu Dewi tadi mau menyampaikan langsung soal blue carbonnya tadi. Atau udah ya, mungkin kita lanjut dulu aja mungkin. Please, sir.
Yeah, okay. So for the first question about MIT scenario, this scenario is the scenario that developed by YASA, by another research group in Austria. And then that mitigation scenario, they embed in the Eclipse emission inventory, which is the emission inventory developed by also that research group. The assumption that they use is they apply all possible control methodology, apply all applicable emission control approach to reduce black carbon and short-lived climate pollutant. So they produce one of the report that if they reduce all of the, if they apply different mitigation scenario, how much of the black carbon and also the other short-lived climate pollutant can be reduced. But in general, those regulations refer to reduce emission from cook stove, like from residential sector, apply the emission to reduce from industry sector. So meaning that all of the sector, the emission will be reduced based on the current available technology. For example, right now, the best technology that we can do is reduce 50% of the emission from industry. So they apply this 50% to the industry, and then they will see, and then they will apply these several mitigation measure into different source, and then see what will be the impact in the future. And the second question, because I'm not familiar with blue carbon, so I'm sorry I could not answer that. But anyway, the model can input any pollutant into the model, and as I told you that we need to also put in the reaction in the atmosphere into the model, because this model is kind of the open to the public model. So you can choose any mechanism in the atmosphere that put into the model. So if you want to reduce this, if we want to model this blue carbon pollutant, then maybe you need to find the appropriate mechanism in the atmosphere that you will put into the model, and then the model can predict it correctly.
So basically, you can input other reactions to that model, sir?
Yes. So there's going to be the different pattern, also different reaction that we can put into the model, and also how reactive of different pollutant that available in the atmosphere, we can also put those information into the model too.
All right. Then maybe, okay, that's great. Maybe this is the last question, sir. A question coming from Mr. Nurendra. He asked, the emission inventory that been used in the model are from within boundary model or use global emission inventory. And also for WRF model, is it compatible for tropical area condition which only have 2 seasonal condition? That's 2 questions, sir.
Okay, so first one about the emission inventory that used in the model, right? And then the second one is about the whether the model is appropriate for this region, right?
Right, in tropical, sir.
Okay. So so the first question, the weather emission inventory that we use is developed only inside the study area or extend to outside the study area. So in this study, we use 3 emission inventory. The first one going to be RCP, right, which are related to the YASA, to the IPCC projection. The second one going to be Eclipse, and then the third one going to be Winijkul that focus on residential. So RCP that we use is the global emission inventory, and then we're gonna be in the study area. We're gonna use more detailed inventory, like the Eclipse and also the Winijkul that we use gonna be within our study area. So the emission inventory that we use are both in the study area and also outside of the study area. But the one that are more detailed gonna be the one inside our study area. Outside of our study area, not gonna be as detailed as the one that we use inside our study area. And then the second question is whether the WorkCam is appropriate to use in the tropical region because we have only 2 seasons, right? So actually, there are a lot of study that we use WorkCam in this study in this region. So I think it's appropriate, and I think I should address in the term that because again there are different type of input that we can put into the model, then maybe we need to do validation before we can use, and then before we can say that the model is good or not, then it totally depend on the input that you put in, and also how good of the comparison with the observation data. But to answer your question, whether it's appropriate in this region, yes, with the appropriate input and also with the validation of the data, output data.
All right. Okay, thank you very much, sir, for your remarkable explanation. That was a quite good explanation about air quality modeling. Maybe Mr. Asep, Pak Asep, masih nyambung? Maybe there is any remarks from Dr. Asep, sir.
Okay. Thank you very much for Dr. Ekbordin. Actually, we are very enlightened with your presentation. So again, thank you very much for your sharing. So I hope we can talking about another topic with you in near future. Thank you very much.
Thank you very much, and thank you for all of the attendance. Also, the questions that are very, very good questions.
Yeah, all right, sir. Maybe you have any final remarks, sir?
For me?
Yeah, maybe you have any closing statement?
Okay, so thank you everyone for today, and then I'm feel very appreciate that today I have a chance to give sharing this type of information with you, because most of the time when we do modeling, we give only the final result and then give it to people, and then people ask whether this data is good or not. But anyway, through the process that we come out to the output, we pass to different process. We need to do like validation. We need to think about what should be the input that we need to put in. And it's good today that I can share those kind of process with you all today. And then so that we can know that what should be the process that we should put into the model in air quality management, so that every time that we have air quality management, we can look into the model, but model is not the only tool that we can use to manage air quality. We need inventory. We need also monitoring. So all of that together, we can have better air quality.
All right. Thank you very much, sir. Finally, we have come to the end of our session. On behalf of the committee, I would like to say thank you very much to our special guest, Dr. Ekbordin Winijkul, for the outstanding lecture about air quality management. Also to our participants for the active participation. Hopefully the lecture will be beneficial to us so that we can develop and explore more about environment study. Terima kasih banyak kepada para peserta juga. Mungkin untuk sesi kali ini kita tutup, kita break dulu sampai pukul 13. Nanti kita pada pukul 13 akan masuk kembali untuk melakukan sesi ketiga materi berupa instalasi dan demonstrasi Qual2K dan WASP. Thank you very much for Dr. Ekbordin. Yeah, you may leave now if you have any other concern maybe.
Okay,
Thank
thank
you
you
very
very
much.
much. So, sawadee everyone.
Yeah,
Thank you
Yeah.
very much.
it's been an honor, sir.